So as we said, the gradient m of a line is telling us how for every unit of change in the independent variable, how y responds, the degree and direction to which y responds to this change in the independent variable. A nicer way to say it is by saying it's the rate of change. It's the rate of change of y with respect to x. That's a nicer way of saying it. So we now know how to find the rate of change of y with respect to x between 2 points. And you on a line, finding the rate of change between any 2 points, as I said before, will always give you the same answer because the gradient is constant for a line. Now let's say that we have a curve. Unlike a line that has a gradient that is constant between any 2 points on the line, a curve has a different gradient for almost every point. So the gradient here is quite likely different from the gradient here, or here, or here. The gradient at any point on a curve is different. Now, we want to find the gradient, let's say at this point here. So we're going to draw a line that touches only that point on the curve. And that line we're going to call a tangent. A tangent is a line that touches only one point on the curve. And the point that this tangent touches, we will call a f of a. Now, the thing is, we have a little complication here because we want to find the gradient of this tangent here because it tells us the gradient of the curve at this point. Sadly, we only know the point a f of a. But in order to find the gradient of a line, as we saw before, we need 2 points. 2 points on the line in order to find the gradient. So what we're going to do, we're going to do a little bit of manipulation. So what we're going to do is that we're going to draw a line. In fact, we're going to draw a number of lines that pass through this point, a f of a, right? And they also pass through another point on the line that we will call x f of x. Now, what we're going to do is that we are going to carry x closer and closer and closer to a by bringing up this line right here. So how exactly are we going to do that? Let's see. So again, we're going to be drawing a line that passes through the point a f of a, and what? It touches the curve at that point, this point right here, and so it's actually x is getting closer to a. So what we're going to do now, again, is to just keep doing that, drawing another line that passes through 2 points, where one of them is a f of a, and the other point is a point such that the x value is closer to a than it was before. So mathematically, what we're actually doing is that we are taking the gradient of this line, which is, let's say, f of x minus f of a all over x minus a. And what are we doing? We are finding the limit of this as what? As x approaches a. And what exactly does that give us? That is going to give us the very line that we started out with. This line. This is going to give us the gradient, rather, of this very line that we started out with, the green line. Because what we're doing is finding the limit of f of x minus f of a all over x minus a as x approaches a. Once x reaches a, we're going to actually end up with this exact line. This is the exact line that we're going to end up with. And so we are not finding, when finding the gradient here, we're not finding the rate of change or the gradient between 2 points as we did before, where we say the gradient of a line is y2 minus y1 over x2 minus x1. No, we're not finding the gradient between 2 points. What we're doing here is that we are finding the gradient at a single point. We are finding the gradient at the point a, f of a. That is where we're finding the gradient. We are finding the instantaneous rate of change of y with respect to x. We are finding the rate of change at a single point. I cannot emphasize that enough. So let me just rewrite this on another page. We are finding the limit of f of x minus f of a over x minus a as x does what? Approaches a. Now, let's say that h is equal to a minus x. If h is equal to a minus x, and we're going to substitute h into this, then what that's going to give us is we're finding the limit of f of x minus, looking at this, a would be equal to h plus x, so it would be f of x plus h all over negative h, and we're saying that h is approaching a, so we're going to end up here with h approaching 0 because h is equal to a minus x, and x approaching a suggests that these would end up giving, this difference would end up giving me 0. So we're finding the limit of f of x minus f of x plus h all over negative h as h approaches 0, which in effect gives us the limit of f of x plus h minus f of x all over h as h approaches 0. So what we call this limit is the difference, D-I-F-F, difference quotient. And this is something that is extremely important for you to remember. You are finding the instantaneous rate of change. And in order to find the instantaneous rate of change, you have to use this. You have to use this expression, the limit of f of x plus h minus f of x all over h as h approaches 0. In the end, we are going to get a number. What that number is the gradient of the curve at that point. It is the gradient of the tangent to the curve at that point too. And we call this limit, the constant that we get upon finding this limit, the derivative. We call it the derivative, the first derivative. And we represent it by saying f prime of x. We also say dy by dx. And we also say y prime. So when you hear people talking about differentiation, what they're talking about is a way, or the way, of finding the instantaneous rate of change, the rate of change at a single point. And the very definition of differentiation is, as I said before, again, I cannot emphasize this enough, the limit of f of x plus h minus f of x all over h as h approaches 0. That is the very definition of differentiation. Now, before we close, since the derivative, as we can see here, is actually the limit of a function, it is safe and reasonable and logical to conclude that where a limit does not exist, then the derivative does not exist. And we learned when we were doing limits and continuity that a limit does not exist at a point of discontinuity. So we cannot find the derivative at a point of discontinuity. So that's point one, that the derivative does not exist at a point of discontinuity. The limit also, no limit exists at a vertical tangent line. And so in this case, the derivative would not exist at a vertical tangent line. That is, when I say vertical tangent line, I'm making reference to some asymptote and a function that is approaching infinity. So the limit would not exist at that point, and as such, the derivative would not exist where at some vertical tangent line. And lastly, the curves that I am about to draw here, we have what is called a kink, and here we have what is called a cusp at the points right here. Those are some odd points, and functions that have kinks or cusps would not have the derivative existing at those points. So for example, one function that comes to mind readily that has a kink would be mod x. And mod x the derivative of mod x does not exist at x equal 0. So yes, so keep those in mind. Those 3 points, those 3 conditions that render the derivative of a function, the instantaneous rate of change of a function at that point, non-existent.